Okay, let's start again. This product pi of d here is the product of f of d's over all divisors of n. This notation pi of d. So now using this, let us see the theorem. For each positive integer n, tau of n here is equal to product of ei plus 1, where p to the power ei runs over the divisors of n. So here how to prove this formula for every positive integer, and tau n here stands for the number of divisors of n. So let n here is equal to, because we know that every integer n can be expressed as a product of prime powers, that is p1 to the power e1, p2 to the power e2 dash dash pr to the power er, which is same as pi or product of pi to the power ei, where I varies from 1 to r. Now let d here a positive divisor, d here is p1 to the power f1, p2 to the power f2 dash dash pr to the power fr be the positive divisors or the divisors of n, with the condition that fi here is greater than or equal 0, means this power, but less than or equal to ei, because all this they divide, and so therefore the power of p1, f1, f2, f3 cannot be greater than e1, e2, e3 and so on. So in general we can say that fi is greater than or equal 0 but strictly less than or equal to ei. For example, if you have n is equal to 2 square into 3 to the power 3 into 5 to the power 1, then divisor d here you can take it as 2 square, 3 square and 5, or you can write 2 square 3 into 5. These are all divisors of n. But you cannot take here 2 to the power 2, 3 to the power 4 and 5. This one 2 to the power 2, 3 to the power 4 into 5 does not divide, and so therefore that's why there is restriction on the powers of this d, pi in d, which are divisors of n, because it should be less than or equal to the powers of this prime powers of n, So here we have fi is greater than or equal 0 but less than or equal to ei. So which shows that this d divides, and if and only if fi here is greater than or equal 0 but less than or equal to ei for all I varies from 1 to up to n. So since this fi may take all these values, may take any of the values, fi may take this value, any one of the values, 0, e1, e2 dash dash er. So there, how many terms from here to here? There are r terms, and with including this one you will get there are ei terms where I varies from r only. Therefore in general, so there are ei plus 1 possible terms for values for f. So therefore there are ei plus 1 possible values of fi. That is, number of fi's is equal to ei plus 1. For example, if you take n is equal to 2 square, 3 to the power 1 and 5 square, so what are the possible values of tau of n here? Tau of n here will be equal, for this 2 square, so fi here, divisor d here you take 2, 3 and 5 squares. So therefore the number of divisors of this one 2 here, what are the possible values of this f1, f2, f3? You can say here in general, this is e1, e2, e3. So what are the possible values of n here, of fi? Fi here takes the values, or for example in particular f1 takes the value, this is if it is 2 here, so it takes the values greater than or equal 0 but less than or equal to 2. So the possible values of 2 here, f1 here are 0, 1 and 2, and the possible values of f2 here, if 3 here you have 3 square, so what are the possible values of f2? It takes the value 0, 1, 2. If 5 cubed here, the possible values of f3 will take the value 0, 1, 2, 3. So in this case you will have 1, 2 and then ei, so it will be 2 plus 1. there are 3 possible values of fi, and here also 2 plus 1, because we can express this n as 2 square, 3 square and 5 cube. So it will be the power of this 2 plus 1 and then 2 plus 1 again for f2 and 3 plus 1 for f3. So therefore in general we have the possible values of ei plus 1 will be the possible values of fi, and the number of fi's, therefore number of fi's equal to ei plus 1. So in general the number of divisors of n, which we denoted by tau of n here, will be equal, because for e1, for p1 to the power e1, p2 to the power e2 dash dash pr to the power er, this is n, and if d is equal to p, which divides n, f1 p2 to the power f2 dash dash pr to the power fr, then what are the possible values of f1? It will be e1 plus 1, and what are the possible values of f2? It will be e2 plus 1. So here in general we have e1 plus 1 into e2 plus 1 dash dash into er plus 1. So therefore tau of n here is equal to product of pi of ei plus 1, where pi to the power ei runs over the divisors of n. So thus we have here, if n is a positive, for every positive integer n, tau of n is equal to product of ei to the power ei plus 1, where pi to the power ei runs over the divisor of n. So note that here you can write as note, if GCD of mn is equal to 1, means they are relatively primes, then the number of positive divisors of m into n stands for the number of positive divisors of m into number of positive divisors of n. So this implies that the number of positive divisors, so this number of positive divisors of mn is nothing but tau of mn according to the definition, and the number of positive divisors of m here is tau of m into tau of n. This is true when the GCD of mn is equal to 1. So thus we can say that tau of n here is a multiplicative function. So that we'll discuss it in the next theorem. So for today's theorem, I'll stop here. That is, what does it state? It states like this: for any positive integer n, that we have tau of n here is called product of ei plus 1, where p to the power ei runs over the divisors of n.